Now in this new video lecture, we are going to talk about something you've probably been waiting for since we started talking about densities and defined the density of the exponential random variable, etc. We'll talk about density of random variables. So an absolutely continuous random variable, you have probably heard this term before, absolutely, and didn't really know why the module leader was insisting so much on this term. We'll see this in a future video lecture that is coming, but it's a lot more than just being continuous. Okay? What we are asking here. Okay, we're not just asking that a random variable has its cumulative distribution function continuous. It is a lot more than that. It is equal to the integral of something. So here's a definition. We say that a random variable x or its distribution or its cumulative distribution function, okay, they are absolutely continuous. Okay, so x is an absolutely continuous random variable. Px would be an absolutely continuous distribution, and fx would be an absolutely continuous cumulative distribution function. Anyway, so it's absolutely continuous if this Radon-Nikodym derivative of the distribution of x with respect to the Lebesgue measure. As usual, dx is just a slick notation for a Lebesgue measure, which allows us to do computations and link all this new notion of measure to what we previously used from analysis and calculus. Okay. So if this exists, okay, dx is the Lebesgue measure on the space being the real line with the Borel sets. This, if in this case, this derivative here, we call this the probability density function of the random variable x. Okay? And usually we denote it by a f, lowercase f, sub-index x. So it's a function from real numbers to real numbers. It's always a non-negative, of course. Well, at least it's non-negative almost everywhere. And so the notation, that's something we need to emphasize here, fx does not depend only on x. Okay? If we have a sample space omega, and we have this map x, which is a random variable to the real line, just that is not enough to determine the density of x. In fact, that is not even enough to determine whether or not x has a density. Okay? We really need to specify a measure here in order to talk about density. Here's some known examples that will make us feel well and comfortable. Okay, suppose I consider this function here, okay, and I wonder about the measure that has derivative with respect to Lebesgue measure. Okay, that's a function evaluated at x. This function has these values. Well, we know if we integrate this function on the entire real line, we get 1. That's quite a tricky computation that we have to do, but we know this gives 1. So this is indeed a probability measure on the real line. And this probability measure on the real line, we call it the standard normal distribution on the real line. And, well, this is the most important continuous distribution, of course. From a practical point of view, because of the central limit theorem. From a theoretical point of view, of course, as mathematicians, we prefer this one here, because this one is clean, simple. So the density, instead of doing something like this, it is just 0, 0, 0, then it's 1, then it's back 0, 0, 0 again. Something very easy to handle and manage. This is called the uniform distribution on this interval from 0 to 1. Or a remark, which is just a consequence of a remark we made before when we were talking about Radon-Nikodym derivatives in general, is the density of an absolutely continuous random variable. It's unique only up to almost everywhere equality. Okay, so the density of we can talk about the density of a uniform random variable if we agree that a set of measure 0 is not important. So what is not important what is the value of the function exactly here or exactly here, because these 2 points alone, they have measure 0. So whether we put them here or here doesn't change the fact that this is the density of the uniform variable. As a matter of fact, we could even have defined these points to be here, and we could even define this point here to be here. If we can always change the function on a set of points that has measure 0, and this won't make any difference because density functions, they are only used when they appear inside an integral. So no property of those functions will make sense if we're not including them inside an integral. And inside an integral, changing the value of the function on 3, 2, 3 points, or countably many points, or even uncountably many points, as long as the total number has measure 0, will not make any difference.